determine the area of the loop in this particular parametric curve. So we've got t squared for the x-coordinate and 4t minus t cubed for the y-coordinate. So area of the loop, which suggests to me there's only one. So we're going to have to find out where this loop is. So what we need to do is find where this curve might self-intersect. So that's the first thing we're going to do. So we introduce another parameter value, s. We just want s to be different from t, but to still have the equations for the x-coordinates and y-coordinates agree. Now we'll just double check that we got this right. Yep. Okay, it seems to me that the first equation is probably the easiest to work with, because we can see a difference of squares. Okay, so either t and s are the same, or t and s have opposite signs. Okay? Well, we need t and s to be different, otherwise you're looking at the same point just with different letters. So we're going to use the fact that t should be negative s and plug it in here. Okay? We will also have to avoid t being 0, because negative 0 would mean that s is also 0. But we'll deal with that if it comes to it. Okay? So we've got 4t minus t cubed needs to be the same as 4s minus s cubed. But that's for negative t minus negative t cubed. So negative 4t plus t cubed. Bringing everything over to one side. 8t minus 2t cubed has to be 0. So 4t minus t cubed is going to be 0. And we factor that. Either t is 0, which would lead to s being equal to 0, so we don't want that. Or t is 2 and s is minus 2, or I guess technically you could say t is minus 2, s is 2. But the point here is that at parameter values of 2 and minus 2, we will get the same point out. Okay? So the curve comes along, it crosses a point at t is minus 2, and then it does something. It doesn't have to be a nice loop, but it loops back. And when t is 2, it happens to cross at the same point. Okay. So our loop, oops, is from minus 2 to 2. Okay. So that lets us set up a formula. We want the area. Okay, so we know how area works. Our bounds are minus 2 to 2. That's what we had to work out. And then we use the y-coordinate. Okay. Times the derivative of the x-coordinate, which was t squared, so it becomes 2t. All right. We'll go minus 2 to 2. We'll have 8t squared minus 2t to the 4. These are pretty easy to integrate because they're polynomials. Okay, so it'll become 8t cubed over 3 minus 2t to the 5 over 5. Go from minus 2 to 2. And we'll do this on the next page. Get a fresh sheet here. All right, so plug in 2. So 8 times 2 cubed over 3. Minus 2 times 2 to the 5 over 5. Minus, and then we just subtract. So negative 2. All right, so we'll have 64 over 3 minus, 64 over 5. Minus negative 64 over 3 minus negative 64 over 5. Okay. So that'll turn into 64 over 3 minus 64 over 5 plus 64 over 3 minus 64 over 5. 128 over 3 minus 128 over 5. Okay, and now we can get a common denominator here. So I haven't simplified the 5 times 128 because it's the same thing on top, so subtracting these we'll get 2 128s over 15. And so the area is going to be 2 times 128, or 256, over 5. And that is the area for the particular loop in our curve.